prefrontal, kind of get an idea how you would do this. We used to do pitting of frogs. Way back when I was going through college, we had frogs in our physiology classes, leopard frogs. And to use them, you have to scramble their brains. So you would take them, bend their head, and take a needle and go in there and pit them. Scramble their brains until you destroy their brain. It's sort of what he was doing, but of course, just part of the brain.
I don't understand how that wouldn't just kill a person.
It's not the whole brain, it's just that area. And that area has these major functions. So it doesn't affect sight or anything because those are all other areas of the brain. So you're specifically only destroying that part of the brain.
Okay, so the entire brain is dead somewhere.
No, just that part.
Okay, so you only have
They
one
can
part
see,
that
they
doesn't
can hear,
affect,
they can.
I
You know,
thought
Jack
it was,
Nicholson, pretty much, he was just a nice guy. Okay, he could do everything for himself, he was just a nice guy after that. Personality, that's kind of what's in that area. Okay, well, enough on the motor areas. So now what we're going to do, I'm going to approach it a little bit different. I'm going to introduce you to a friend. Oh, by the way, don't forget, this is on the D2L. The numbers relate to Victor Victoria. If you want, you might want to put the letters on the other one. Okay, I want to introduce you to a gentleman. Okay. He's called Mr. Homunculus. Okay, Mr. Homunculus. You can tell he's a little bit weird person. Huge hands, huge head, tiny body. Okay. What we're going to talk about now is the kind of the organization of the brain. And we're going to look at what's called, on your handout now, we are on the area that says functional organization. Okay? So this is Mr. Homunculus. But that's how you are represented on the brain. That's you represented on the brain. So let's look and see how that would look. Okay, this is not from your book, but this represents the motor cortex, the other side, the sensory cortex. So we're just looking at those two parts. Okay, and obviously, there that homunculus is, it's kind of all spread out. Okay, so here's the big head on each side. So what we're going to do, we're going to do an experiment. Okay, so basically, this is the sensory cortex on the left hemisphere. Now, there's a sensory motor on both sides. But we're just going to do this experiment with the sensory on the left hemisphere. See up there. And on the right hemisphere, the motor. So you all remember, maybe not, Hannibal the Cannibal, and the last scene where he had this man sitting there and he'd taken his skull cap off, and he had a spoon, and he was dipping the spoon and feeding this guy parts of his brain. I've ruined the ending of that, probably because you don't want to see the movie. Okay. That did that hurt the guy? Was that painful when he took a scoop out of the brain? No, because the brain has no pain receptors. You get rid of the duramater, the brain itself, you can punch on it all day long. It's not going to hurt. Okay? And is it, is that science fiction that someone might do that? Open the brain, put the guy alive and awake? No. Surgeries on the brain, very often, they'll remove a section of the skull, duramater, all the time this guy is awake, and then they'll operate, and they'll be talking to the guy while they operate, because they want him to respond. And they ask questions and so forth. and say, well, what do you feel, that type of thing, because they don't want to hit something they don't, aren't supposed to hit, okay? Well, what we're gonna do, we're gonna get that guy sitting there, and we're going to stimulate with an electrode different parts of the brain, okay? But specifically only on the sensory motor cortex. So he's sitting there, we got our electrode ready, and the first thing that we're going to represent or look about is the spatial representation. So Mr. Homunculus, you see up there, different parts of his body is related to different parts of the tissue, the actual tissue, okay? So, let's find out what happens on the sensory. I'm going to take my electrode on the sensory cortex and I'm going to stimulate it right there. Zap. And I'm going to ask him, okay, anything? He says, yeah, you're touching my thumb. I'm not touching his thumb. I'm stimulating the area that is receiving messages from the thumb. So it's hooked up with the wires, basically, right there. Okay? So I don't have to actually touch his thumb to make him feel like I'm touching his thumb. Okay? So I could do this on anything. I could touch him on any part of his body by just stimulating any of these. He'd say, ooh, now you're touching me there, now you're touching. Okay? Let's go over here. What happens over here? Okay, I'm going to choose this one right there. I'm going to stimulate this part of the motor cortex. And he's not going to try, but his toes will twitch. I'm going to get his toes to twitch. To move. Okay, and I'm not telling him to do that. He has no control. It will do. It will twitch. Okay? So I could do this on any parts, and I could do any part of the body, I could get a muscle twitching and moving.
Well, could you
Facial.
make him speak or just make his mouth open?
We make him speech, basically, but he would have a movement of muscles. You know, it'd be kind of hard to do enough to make a word. Okay? Well, that's one aspect. Another aspect is contralateral representation. So we're going to do this experiment again. I'm going to go back and I'm going to stimulate right there. Now remember, this is the left sensory cortex I'm stimulating. Okay? Now I was going to say, okay, what's happening? He'll say, well, you're touching my thumb. I said, okay, can you be more specific? You've got two thumbs. Which one? He'll say, my right thumb. Even though I'm stimulating the left brain, it feels like I'm touching his right thumb. So all the sensory information is crossing over, contralateral. So this side of the body is represented over here and vice versa. Okay? What's going to happen over here, you probably already kind of know. I stimulate this, and that's the right sensory motor cortex, so it's his left toes that are twitching. Contralateral. Well, that still doesn't really tell you why you've got a big head with big hands. So that's differential degree of representation. Okay, so how does that work with the sensory? Okay, what we're talking about is how sensitive are certain parts of your body. And one of the ways you can tell parts that are more sensitive than others is to perform a 2-point discrimination test. So I got these two little sticks really close together. And I can touch my lips feel both. No problem. I can feel both. There are places on your body where I can put this like this, if I press them simultaneously in this area of your body, you will feel like I'm only touching you in one place. Your two-point discrimination would be really bad. So where do we have the best sensory feelings? In the face and the hands. So that's why you have more tissue allocated to the face and the hands, because they're the most sensible, I guess you'd say, receptive to touch. Where other parts of the body, you know, here you've got all of this is just the face. You've probably got as much tissue just for the lips that you do for your whole back. Okay? For reception of touch sensations. That's how it works over here. What happens over here? What areas of the body do you have the most finer muscle control? Hands and your face. Facial expression. You know, how many different types of facial expression can you do? I mean, there's, and all the activities that you can do, fine activities with the hands. So what that means is you have more tissue. When you put the hands and the face together, there's not much tissue left for the rest of the body. Very little. You know, but you don't need it. You don't need that fine motor control for your legs. Okay, so you don't have that much tissue. So this is differential degree of representation. So that's how this homunculus is set up. Okay, so that's the organization. We're not going to talk about what side of the brain is dominant and so forth. You know, it's not, you know, exactly related to whether you're left or right-handed. Usually it's the left brain. What I want to say is one of the things that's really fun to play around with is something called the split brain experiments. The split brain experiments, and I'll explain a little more later, but they really, really show that the right brain and the left brain are not the same. Did you know your left brain talks, your right brain cannot talk? And there's a bunch of others. I could lecture for a whole hour on this. I got tons of stuff on it. But we don't have time for that. But if you look up split brain, it's amazing. You know, it's a certain type of experiment that shows what the right brain, left brain does. Like the left brain is mathematical, the right brain is esoteric type thing. A lot of people want to say women have more of a right brain functions, where men more left brain. You know, a lot of ways you can look at this. But, you know, I'll mention this again here shortly. Okay, so that pretty much takes care of the cerebral cortex. We're through the cerebral cortex. So now what we want to do, the next there is cerebral nuclei. Cerebral cortex is gray matter. It's outer gray matter. But there is an inner portion called the basal ganglia. Okay, which gray matter. So we're not going to really do much with it, but it mainly is to coordinate gross motor activity. Okay, walking, sitting down in some place in the range of your body. Doesn't take much control. You know. Gross motor activity. So if you want to kind of visualize what those that basal ganglia do, think of somebody with Parkinson's disease. Okay. Muhammad Ali has Parkinson's disease. How does he walk? He shuffles. He doesn't walk. Okay? He doesn't have good control of that. Nothing wrong with his mind, but motor control. Okay? Also, people with Parkinson's shake. when do they shake? So when the parking stands in front of you, depending on severity, they shake until they start moving. They started moving around, they stop shaking. So it's only when they're not moving with their hands, they shake. And one little story of this, kind of interesting, was up on the internet a couple of years ago. They put a man with pretty severe Parkinson's on a bicycle. Put his feet on the bicycle, the pedals, gave him a little shove, and he was able to ride the bicycle around the block, no problem. Any cars passing by would not have ever known he had Parkinson's disease. But he can't stop because he stops and falls over. So it's not, therapy, but it gives freedom to people who have Parkinson's to be able to know that, I might be able to ride a bicycle. Just, exercise. Okay. That takes care of the gray matter. So now we have one place left, and that's the white matter. And this is not from your book, but it's similar pictures, and it's got the little things I need to have on there. Okay, so we're looking at the cerebral medulla, which is white matter, and remember, white matter are pathways. White matter are axons. White matter are nothing more than ways of connecting two gray matter areas. Two gray matter areas can communicate to the white matter. So they're pathways. Okay? Now, we're looking at, let's just look at the left cerebral hemisphere. It has three types of communication that it has to perform. Okay? One, it has to talk to itself. And you know that. Everyone talks to themselves a lot. Okay? Well, the left cerebral hemisphere has to talk to itself. The gray area up here needs to communicate with the gray area back here. So there needs to be pathways between those.